Hi everyone, in this video we're going to be going over some rectangle properties, and we're going to go over applying these in some numerical examples as well. So what we're actually going to be doing today is in your flipbook you want to make sure that you are lifting up all of the flaps that are in yellow. So you should be lifting up that parallelograms tab and you're writing under it. You should see the word rectangle on the flap. At the very bottom you should see the word rectangle. Now, this next shape, which is rectangles that we're working with in Unit 6, is a specific type of parallelogram. Now, if we backtrack a little bit, in the last lessons, we learned that a parallelogram was a specific type of quadrilateral, right? Now we're going an even step further. Now we have this shape that is a specific type of parallelogram. Now what this means is that it's inheriting the properties of a quadrilateral, a parallelogram, and there are a few more properties that help us classify it as a rectangle. So there are a few unique things that help differentiate just a regular old parallelogram to a rectangle. Now, you want to divide your notes up into 3 sections. So you're going to have properties. We're going to eventually fill in how to prove it. We're going to do that in the next lesson. And then we're going to have some numerical examples. So you want to make sure you're writing tiny so that you can fit everything and so that it's legible for you. Now, in an effort to save some space, under properties, instead of actually listing out the properties of the quadrilateral and the parallelogram, you can just write this. You can write all properties of a quadrilateral and a parallelogram. However, you are responsible for knowing this. So you need to know these properties. You can't just let them get lost in the sauce. So that's why I emphasize to you guys, every time we do a new shape, you should spend about 5 minutes just studying what all of those properties are, so that as we go down the family tree, you don't have much more to remember. Because guess what? If you already know all the properties of a quadrilateral and a parallelogram, for a rectangle, you only need to remember 2 things, which is not bad at all, right? But on the contrary, if you didn't remember all of these, then it's almost like learning like 7 or 8 properties, which is kind of crazy. So the things that make it unique, the things that help us go from a parallelogram to a rectangle, is that our diagonals are congruent and all angles must be 90 degrees, right? So I kind of, I attempted to color code it, where here are diagonals. So our diagonal BD is congruent to diagonal AC in this case. And it gets a little confusing to label, so I didn't really label it, but I wrote this little symbol over here. Now again, if we just know that a shape is a parallelogram, this is not always true, right? The diagonals don't need to be congruent, but if there is a parallelogram where diagonals are congruent, we know that we have a rectangle, right? And same idea, if we have a parallelogram where all the angles are 90 degrees, right? We know that that's going to be further classified as a rectangle. Now, please note, I didn't make the first diagram too crazy, and I want you guys doing the same exact thing of drawing 2 separate ones, because in this diagram, these are just the new properties labeled. But in this next picture here, we don't want to forget about all of the properties of parallelogram and quadrilateral holding, right? So we have a parallelogram. We know that our opposite sides, both pairs are going to be parallel, right? We also know that both pairs of opposite sides are going to be congruent as well, right? So we have those labels. We also know that the diagonals are bisecting each other, right? But now this is interesting because I always tell you guys to differentiate with your tick marks, right? So this tick mark would kind of mean that this portion here is congruent to this portion here. However, I usually always tell you to differentiate, but the fact that the entire diagonals are congruent, right, mean like if that whole entire red diagonal is congruent to the whole blue diagonal, that means that when they're split, all of the 4 pieces are going to be congruent to one another, right? So this is actually an interesting situation, because when we had parallelogram, you guys don't need to draw this, but when we had a parallelogram and we drew our diagonals, we had to differentiate between the congruent pieces by going like this, right? But if we know it's a rectangle, we know that those entire diagonals are going to be the same length, so when they're cut in half, all of those values are going to be the same as well. All right, awesome. Now in this next slide, we're going to go to the family tree tab, because again, we're adding on to our family tree, so make sure you're lifting up every tab. You're lifting up the squares tab, and you should be writing on the family tree. So far, we have quadrilaterals at the very top of our family tree. Now, the branch that we're going, so we just did that parallelograms were one type of quadrilateral, right? Now we're breaking down parallelograms. So right here, we can put rectangle. Now again, what I want you guys to realize too is that when you're using the family tree, how I want you to think about it is, if you're going up the vines, like if I go from rectangle Like if I'm at rectangle, I know it's inheriting all of the properties of the things that are coming above it, right? So it's kind of a good way to think about it. The family tree is easy to like remember writing down. So I'll usually like to like locate my shape, and then I'll remember, or I'll try to go up the family tree to figure out what properties that like our rectangle actually has, right? So as you can see, there's one other branch for parallelograms, and we're gonna get into that in the next video, or in the next two videos. So we're going to get into two numerical examples today. And again, when you're doing any numerical example with quadrilaterals, any four-sided shape, you want to think about what property we are using. And this isn't just for four-sided shapes either, right? This is for like triangles, and when we did parallel lines as well. Whenever we're doing a numerical example, we need to think about which property is being addressed here. So as shown in the diagram of rectangle ABCD, now this is huge. The fact that it tells us that it's a rectangle, I know that I can use any of those properties that we just listed, right? Otherwise, if it didn't say it was a rectangle, we wouldn't be able to do that. But it does tell us that, so this is a great deal of information here. We're happy with that. It says diagonals AC and BD intersect at E. It says that AE, which is over here, is x plus 2, and I even like to sometimes put those brackets there. And it says that BD, which is this entire thing, is 4x minus 16. And it wants the length of AC. So it wants the length of this whole first diagonal over here. Now I know, like, I'm not going to be able to do anything right now to solve for AC. I know my first step, step 1, is to somehow solve for x. Now, in order to solve for x, this is when I need to think about, okay, what property am I going to be using? Well, we know a few things. Like, I know we're dealing with a property about the diagonals of a rectangle, because the only two unique properties we have are that the angles are all 90 and that the diagonals are congruent, right? So this question isn't really talking about angles. So I know I'm going to use property number 2. I know I'm going to probably end up using the fact that diagonals are congruent, right? This is huge. And I know this is a dead giveaway because otherwise it wouldn't matter that it was a rectangle. Like, it's telling us that it's a rectangle because we're going to be using the fact that diagonals are congruent. Now, another thing that I know, right, a rectangle is a type of parallelogram. So I also know that diagonals are bisecting each other. So that might be something, I'm writing it down because that might be something, bisect each other. That might be something that we need to use eventually here. Okay, so I think I want to color code this. Let's make this diagonal, let's make that information blue. So 4x minus 16 is the whole value of BD. So I think my first method, and there might be multiple different ways to do it. You guys might see a way that I'm not seeing. But my first thought is that I know that my diagonals are bisecting each other, which means that all of the pieces, like if I just look at diagonal AC for a second, I know that if this piece over here, if AE is x plus 2, I know that this piece over here is also can be labeled as x plus 2, right? Because my diagonals, when they bisect, they're getting cut into two congruent pieces. Okay, so I'll check that off since I used it, right? I went ahead and labeled EC as x plus 2 as well. Now, I think what we can do is use the fact that the diagonals are congruent. So again, I know for a fact that AC, which is one diagonal, is congruent to BD. I know that for a fact. Now I need to think about, a lot of these questions are, how can I make an equation to represent this, right? So I know the entire diagonal AC, I can make an expression for that if I just add these two pieces up, right? So if I do like x plus 2 plus x plus 2, if I just add both of those pieces, that's going to give me the entirety of AC, right? So x plus 2 plus x plus 2 equals, now because I know those diagonals are congruent, equals the 4x minus 16, right? That was the value of BD that the question gave us that we have in blue. Maybe I'll highlight this, I'll underline this in blue because it comes from this entire diagonal. Now we can do some algebra. So here we want to combine our like terms. So we have x, and x is going to give us 2x. And then we have 2 and 2, so 2x plus 4 equals 4x minus 16. What we can do is subtract 2x to get 4 equals 2x minus 16. I'll add 16 and add 16 to get 20 equals 2x. And then if we divide by 2 on both sides, we will get that x equals 10. Now, some people might get happy and be like, woo, there's my answer, but we are never content with that. We need to go back to the question and ensure or figure out what the question's actually asking you for. Well, it's asking us for AC. So I like to keep very organized. Now, my second step, and if I had more space, I would literally write it right under all the work we just did, but I don't have much space. So now here I'm going to solve for AC. So AC, again, was represented by us adding these pieces here. So when we simplified that, we got 2x plus 4. Now I know my x value is 10, so if we do 2 times 10, that should be a 10. 2 times 10 plus 4, that's going to be 20 plus 4, which simplifies to 24. Another way you could have done it, right, if you solve for x some different way, what you could have done is solved for AE, and if this is confusing you, you can just skip this, but if you want to see a different way of doing it, you could have solved for AE first, and that would have been x plus 2, which would be 12. And then you know that your diagonal is being bisected, so you have to just multiply that by 2 to get the whole thing, which again would give you 24. So no matter which way you see it, we still have to solve for x first using the properties, and then we got to substitute in there. All right, last question. This one's going to involve angles of our rectangle. So it says, in the accompanying diagram of rectangle ABCD, the measure of angle BAC, which is over here, let's be very careful with how we're labeling these things. So when we label angles, we have to put them inside, right? So 3x plus 4, and then we have the ACD, which is over here. ACD is this bluish portion here. And then that's going to be equal to x plus 28. Now, it might not be so direct what you need to do. However, just from highlighting what I've highlighted, I see a Z shape. And I know, right, we got to get in the habit. We have a rectangle, which is wonderful and great, but we know that a rectangle is a type of parallelogram, right? So we can do a few things here. You could list the properties that you see, like you know that all angles are going to be 90, right? And that's great that we know that. But that might not necessarily help us right now. What's going to help us is going one step backwards. So remember, we have a parallelogram, right? A rectangle is a type of I'm spelling this so wrong, parallelogram. Don't mind that G right there. But we know in a parallelogram, right? We know that both pairs of opposite sides are parallel. We also know they're congruent, but that doesn't really help us right now. So if we went ahead and actually labeled that, right, if we labeled like this side, if we labeled AB being parallel to CD, and we labeled BC being parallel to AD, right, we know that when we hear parallel lines, we need to be thinking about our angle pairs. We have our Z angles, which are alternate interior angles. We know those are congruent. We have our C angles, which are same side interior. We know they're supplementary, right? This is just prior knowledge, and if we don't know this, we really have to spend the time to enforce this. But again, I highlighted it on accident just by labeling my angles, but I see a Z shape right here. I see a Z shape right there, right? And we know that when we look at the inner corners of our Z, when we have parallel lines, we look at the inner corners of our Z, those alternate interior angles need to be congruent. So right now, we know, obviously, like our first step is to solve for x, but again, it's okay, what property, what knowledge am I using to make an equation to help me solve for x? Now, again, we know that our alternate interior angles are congruent. Now, congruent is just another word for equal, so I know that my red angle that I've labeled, right, that 3x plus 4, should be equal to the bluish purplish angle that we wrote, which was x plus 28, okay? Now, again, this is just algebra to solve for x, so we subtract x. I'm just going to use red now. We'll subtract x, and we get 2x plus 4 equals 28, and then we subtract 4 on both sides, and we get 2x equals 24, and if we divide by 2 and divide by 2, we will get x equals 12. But the question doesn't want x, right? Again, do not get, like, too excited that you finished solving for x, that you box it right away. We need angle CAD. Now, angle CAD, trying to use different colors here. Angle CAD is this green one that I'm highlighting right here. Angle CAD is this green one that I'm highlighting right here. So I know, right, we're actually going to use this. I didn't even realize that we're using this, but we are actually going to be using this. I know that in its entirety, right, this angle right here and the green angle that we've just highlighted, I know that together they need to make 90 degrees, right? And I have an x value. I know x is 12, so that means that I can actually find angle BAC. I can actually find this portion. I can find what that angle is. So BAC is 3x plus 4, and I know that x is 12. So 3 times 12 plus 4 is going to give me 40 degrees. And I'm going to actually go ahead and fill that in. I know this is 40 degrees. And remember, together, this angle and this angle together need to equal 90 because we have a rectangle. If we didn't have a rectangle, we would not be able to use this property. So knowing that it's a rectangle is huge. Now our third step is to find angle CAD. And now what I'm just going to do here, I'm just going to do 90 minus 40. Because I know in total, those angles need to add to 90, and I already have 40 degrees. So to find the missing piece, we do 90 minus 40. And we always want to get in the habit of stating our answer. So angle CAD, or measure, since they state it like that, measure of angle CAD is 50. And then we would go ahead and box that answer. So some of these questions might be multi-step, but figure out the properties you're using. If there's an x in there, you're always going to need to solve for x first, and then you might have to do something with that x value depending on what the question is asking you for.